the Newton's laws of motion. The first law, as we are familiar with it, states an object remains in a state of rest or uniform motion unless an external force acts upon it. External force in this sense is essentially a way of bringing in a concept called force to tell you what a force would look like when it acts upon it, or more precisely. So, let us now move on to Newton's second law, which states that the force acting on a body is equal to its rate of change of momentum. Okay. Now, if the momentum of a body, a p, is equal to mass times velocity, if the momentum of a body is changing, then the force acting upon the body is equal to dp dt. This is our common notation of a derivative. So, the rate of change of momentum of a body is exactly equal to the force acting upon the body. This is a mathematical statement that captures the essence of the Newton's second law. Now, we would like to, whenever we state the rate of change of momentum of a body is 0, if dp by dt is 0, then f is 0. If you think of this, this is essentially our first law of motion and this is our second law of motion. So, the first law follows from the mathematics that is used to describe the concept captured in the second law. So, a second way of thinking of the Newton's second law is as the rate of change of position, that is written as velocity equal to dx dt, where x is the position vector or position of a body. So, we first know the position of a particular object. Think about all the quantities that we have in red ink on this slide: mass, velocity, mass, position, velocity and time are all measurable quantities. Force, as a matter of fact, is not independently measurable without measuring one of these quantities. So, Newton's third law that we know, that says that every action has an equivalent and opposite reaction. So, let us look at what this means for us in the context of engineering systems and mechanics. If you think of Newton's third law, it says that if I have an action force, there is an equal and opposite reaction force that is generated. So, a simple way of thinking of this is the wall example. So, I take a block sitting at rest on a frictionless surface. If I exert a force of some magnitude f, this block is going to begin moving to the right. This is again fairly intuitive. We are going to look at this in a more quantitative way a little later. But if I want to keep this block from not moving, there is only one way of making sure that the block is either not moving or moving in a state of constant velocity, and that is by exerting a force that is exactly the same magnitude F in the opposite direction. Okay. If I now took this system and let us say I cut this system in the middle. So, before I cut the block, there were two forces that were into two halves. I will call this half 1 and half 2. If I look at what is happening at the interface between these two, if a whole at just the first part, if I now have a force F acting on the first part and if this piece is in equilibrium, that automatically means that there is an effective force F acting in the opposite direction on this piece that I have titled with Roman numeral 1. Likewise, if I now take the other half, this was already the external force acting on the block, there is an equal force, but in the opposite direction acting on the piece number 2 as well, and these two forces if you notice are essentially inside the block and they are equal and opposite under all circumstances. As long as law to the first law, you can now look at the third law as essentially first law applied to pieces of a larger system. So, if the first law is applicable to a block, then the third law comes from the fact that I will apply the first law to every piece of that block, which produces these equal and opposite forces. Second, so this is kind of a brief introduction to understanding Newton's laws of motion, but I want to close by talking about so let us say I have a line on which I want to define a number line. How do I go about it? The very first act of defining the number line is to define a 0, right. I need to mark a point on this number line and mark this as my origin or 0. After I define a 0, I need to define what I call 1 unit. Right. I need to define a 1, what I mean by 1 unit. And the moment I define 1 unit, I can use other rules of mathematics to define a 2, I can define a 3 by simply saying that I add 1 unit to the previous unit and I get the number 2. So, the fact that the first law, Newton's first law defines what 0 force would look like, the next thing to do is to define what my -1 would look like, which is what would give me the complete number line. So, I can define a -1, I can define a -2, -3, etc. So, you could think of the 3 laws of mechanics as being analogous to the rules we use to define a number line, that we invoke what is our origin, what is a 0 and define what a unit distance is. So, it is kind of like defining a system of units to measure force as a matter of fact, and then defining what the negative of the force would mean. And these are concepts for a scalar number. Now, we will learn later on that force is actually